In the next subsection, we'll see a few more applications of suffix trees. In a way, we've just done the warm-up so far. The real power of suffix trees comes with this additional trick that they make possible. And that enables a few more applications where, again, if you see them first, it looks like this can't be possible in that linear time. But this makes it possible, these longest common extensions. I'll explain what that is in a second. So we've already made use of that implicitly without me telling you and without you noticing, probably. But you can formalize the following problem on a string, the longest common extension problem. You're given a string. Now the deal is that you get this string up front, as in string indexing. So you can do pre-processing on this text. And then later I'll ask you LCE queries, longest common extension queries, which means I'll give you two positions in that text. One here, one there. And you have to tell me how many characters can I read from there to the right that match. So how far can I read the same characters here that are equal? And all I want to know is how many characters, so not the actual text. That's the formal definition here. The LCE query for I and j is the largest L, so that if I read from I and from j for L characters, I get the same string. And because it's the largest L, it means if you take one more character, there's a mismatch. So the next one would be a different character at the two places. And you see how this is connected to what we've done before in terms of the longest common prefix of suffixes. Indeed, it's the very same thing. If I ask for the longest common extension at two positions, I could also say I ask for the suffixes starting at these two positions and how many characters they have in common. So that's really just a different name for the same thing. So let me draw my favorite picture again. I can take this ti, and I can take tj, which starts here, and align it below ti and tj. And then I can ask how many characters here are equal before I get a mismatch. So these two things are the same, just a different name. And we've also already seen the second equation, which relates this to the suffix tree, namely the longest common prefix of any two suffixes. So any two suffixes corresponds to some leaves in the suffix tree. And then I can find the lowest common ancestor of those two in the tree, and that will give me the string depth of that node will give me the longest common prefix of those suffixes. So if I take the lowest common ancestor of those two, it's a boring example because they have the root as the first thing where they join paths if you move upwards. So their longest common prefix is empty. They differ on the first character. And because this is banana ban, the entire thing, and this is naban, the first character is different. We've had the other example before with 5 and 7, where the lowest common ancestor was this node. So they had a longest common prefix of length 1. Okay, so you already know what I'm telling you here. It's just throwing in another piece of vocabulary in the mix, which is sometimes a bit more intuitive because it doesn't talk about suffixes. This observation, I mean, you can express this as this formal equation. I circled it because that's kind of a good one to memorize, just so you can quickly recover that fact, even if you don't remember. You would always have to draw an example and rediscover it. Otherwise, you can also memorize it. That's why I circled it again, but it's the same thing. So we defined a problem, okay? The problem being I give you the text And later I'll ask you lots of these LCE queries, and you're supposed to tell me very fast how many characters these two places share. How can we solve that problem? There's different, more or less smart solutions. If I have the suffix tree already, I could use this last part and find the lowest common ancestor. So I could walk up from both nodes and keep checking if I found the same node. That's one option. Unfortunately, that's quite slow, at least in the worst case. If you imagine you're like in this, like for these two leaves, you're far away in the tree and you have to essentially walk all the way up to the root. Another option would be you pre-compute all those lowest common ancestors in one big table. But because you have n leaves, it would be for every pair of leaves an entry. So that's quadratic space. And even to just write that table to memory, you need quadratic time. So that's too slow on the pre-processing. There's another for LCE. If you use the other version of the problem, there's of course another solution that doesn't do any pre-processing, but instead at query time you're given these two positions, and so you keep walking to the right from both until there's a mismatch. So you just compute LCE naively at each query time. That is fast for the pre-processing because you do nothing. But at query time, you essentially have cost as much as the answer is. So if L is your answer, you would have cost of L. But in the worst case, that indeed is again linear. So it kind of gets you into the same ballpark as here. So both seems it's not so great. Now, without a further trick, you don't really get further. But there is another trick you can play. There's a way to compute for any leaf, any two leaves in the suffix tree, their lowest common ancestor in constant time, after spending some pre-processing, but not this super slow quadratic time. Again, linear time is enough. So in a way, you can compute the suffix tree in linear time, and you can do this pre-processing for lowest common ancestors also in linear time. And then you can jump from any two leaves in one step, in constant time at least, to the lowest common ancestor. And if you do that, you can use the translation that LCA was the same as LCP was the same as LCE to compute longest common extensions in constant time. That's this box down here. So for the rest of this section, we'll use this as a black box. Now, this black box will also crack open. That will be the Christmas lecture. So I wanted to show you what is inside that black box. But I felt it's pushing a bit too far for exam materials, so that will be kind of just for your enjoyment. But that's Unit 9. So for now, that's also a promise. It'll be the last black box, I think, that I'll throw at you. For the moment, let's just take it as given and see what we can do with this. And the first application that uses this is something where we want to find approximate matches. So far, whenever we talked about string matching, we were interested in finding exact occurrences of the pattern in the text. And there's many applications where it's desirable to allow little typos and so on, or a bit of noise. And the simplest version of that problem is the K mismatch matching problem. So similar to string matching, you're given a text and a pattern, but you're also given a bound on how many characters you're allowed to mess up and still call it a match. So formally, we say a match is some position of the text of the same length as the pattern, where the Hamming distance between that portion of the text and the pattern is at most k. So at most k characters are in mismatch. You've heard about Hamming distance when we talked about Hamming codes in Unit 6 in detail. So here it's just a reference back to that. But really it's k characters don't match. Okay. First, what are the simple solutions? You can take our good old brute force method for string matching and adapt it to this. The reason is the brute force method took every possible position in the text and said, let's see if I start here, can I find the pattern there? And you have this inner loop that just compares all the characters. Now in this inner loop, instead of comparing the characters and stopping as soon as you find any mismatch, you can keep going and count the number of mismatches in the same time. So the same time as brute force string matching, you can also do this problem and determine all the matches where there's at most k mismatches. But if both your text and the pattern are fairly long, that's not so great. And we can do better. So we do a pre-processing on something like the generalized suffix tree again. We take the text, append some end of word marker, and then the pattern and a fresh end of word marker. And we use this, this LCE data structure that I've just told you about as a black box. So we can find longest common extensions in this string in constant time. And that in particular means if I have my text and then the pattern afterwards, I can pick a position in the text and I can pick a position in the pattern. And in constant time, it tells me how many characters are aligned or how many characters are the same here. Okay? That's what we'll use. And for that, essentially what you need is the generalized suffix tree and all the string depths and the constant time lowest common ancestor, LCA data structure. But we'll just work with LCE for now. So any two positions you're given, you can find in constant time how many characters are the same. And with that, you can so you can use this simple algorithm that got called the kangaroo algorithm because it always does jumps. So how does it work? You have your text and your pattern. It has aspects of the naive string matching algorithm, the brute force algorithm, in that it goes through all positions in the text where the pattern could occur, so all guesses. So then we have a portion of the text, but now we're trying to speed up the matching to see whether or not there's at most k mismatches. So we count the number of mismatches. We have a position in the text and in the pattern. And as long as we haven't exceeded our budget of mismatches, we compute how many characters from this position in the text and the pattern match in one go. So starting from here, let me make the pattern a bit longer so that my kangaroo has more room to jump. So we start at this position, and now we ask how far can we jump, where what I jump over is characters that are equal. And that's the longest common extension of these two positions. It's the longest piece I can read from there to the right where all the characters are equal. Necessarily, one place after that will be a mismatch. Otherwise, we would have jumped further. So after jumping over these L characters, I go one more ahead. So I move forward by L plus 1. So I'm now standing right behind this mismatch. And I count, I've made one mistake so far. Then I jump again using another LCE until I find another mismatch. And then I'm standing right behind that. By doing this, I can do at most k steps, and no matter how long the pattern is, after time proportional to k, I know whether I found the end of the pattern. So I could match the entire pattern with at most k errors, or not, because I'm still in the middle of the pattern. I ran out of mismatch budget. So the algorithm is fairly simple. The only tricky bit is in the implementation of LCE, the black box for Christmas. So the overall time, instead of the brute force method, was n times m. We now brought this down to n times k. And k is a parameter that you give as a user. And usually k will be small. I mean, if you're trying to find a match because someone is searching something and they might make some typos, but if they've typed 20 characters wrong, then it's probably not a useful match anymore. But probably k is 2 or 3 or so. So this is essentially close to linear again, whereas this, if the pattern is long, might be substantially bigger. And we need this pre-processing, but that's n plus m. That's essentially, again, linear time. So for small k, this is a substantial improvement, and is also a practical algorithm. Now again, I often have these kind of extra sections, state of the art. Maybe I should at some point generally say, whenever it says state of the art, you can ignore it. That doesn't sound like a very, very helpful statement, but you don't need to know it for the exam. People pushed this further, so just in case you were wondering if that's best possible, it's not. You can play further algorithmic tricks, but I don't want to get into those. All right, so that's an application that doesn't even use suffix trees explicitly. They're only occurring inside this LCE query, hidden from you in that sense. The algorithm around it is fairly simple, but it gets the running time down substantially. And a last application is related to that. If you're trying to find patterns and you have a don't care character. So wildcard in this case, it's not like the star in the Unix shell where it can stand for an arbitrarily long string. It's a single character, but you don't care which one. You can do essentially the same as this kangaroo algorithm. A slight twist on that solves that version of the problem. And if you're still curious about more, I brought this book here as well that's on the slides. It's kind of the suffix tree Bible. There's a lot of more applications of suffix trees where if you try to solve it from first principles without using existing data structures, it seems it's very hard to solve efficiently. And with suffix trees, potentially using this trick for lowest common ancestors, it's a relatively simple task to solve them. So the suffix tree in that sense really is this threshold invention that made a lot of other things very simple conceptually, and has lots of applications whenever you have these kind of strings, and the book focuses on biological sequences. So to wrap up, suffix trees are great from a theoretical perspective. They're linear time and space. You can construct them in time proportional to the length of the text. They use up space proportional to the length of the text, and made all these problems solvable, as I just said. From a practical perspective, there's still a few things that are kind of leaving wishes open. The original algorithms for constructing suffix trees, while there were linear time in theory, they were still relatively slow and also complicated to implement and to explain. And the suffix tree itself, because it's this tree with potentially many children and so on, it's a little less obvious how to represent it space efficiently. Think about it that way. We always assume in this section that the alphabet is finite and not crazy big, but it might be all ASCII characters, at least 26, or maybe all Latin characters, all ASCII characters 128 or 226. So it's in the dozens or hundreds. Now you have two options how to represent a node. You can represent a node with an array of child pointers. So it could be something like this. Then every node needs space sigma. If sigma is constant, that's linear space, but still it's a factor of a dozen or 100 overhead. The other option would be some other data structure within each little node that tells you what child pointers exist. So you could have, for example, a little binary search tree over the labels. And then it's a little dictionary in each node that maps from the edge label to the child pointer. But then you have a log sigma space overhead for each traversal, because that's the binary search tree. So here you have a sigma space overhead. Here you have a log sigma time overhead. It's just not clear. I mean, both is maybe fine, but if sigma is not tiny, it's both are not negligible. And even this version still has a lot of pointers. So it's in a way as great as is from a theoretical perspective, but if you implement it, it's still not as good as one would hope.